Hello, these are the Exam 4 review slides for the fall 2018. So this is going to be talking about primarily things like E1, E2, SN1, SN2 reactions, as well as the carbohydrates. So to start off, right, so we're going to be looking at the doing E versus Z. So you come in here and you say, okay, I am looking at, you're going to compare what's hanging off of this carbon compared to what's hanging off of that carbon. So we're going to look at the red carbon first, the two things hanging off here, right? And we're going to use the same rules for determining the priority as we did for doing R and S. So here we're going to be looking at chlorine versus nitrogen. In this case, right, so chlorine is heavier than nitrogen, so this is going to be the higher priority, this is going to be low. So then we're going to look on this side. And for here, right, we're going to compare that versus this, right? They're both carbons. Right? They both have two bonds shown, so they're both going to be CH2. But since they're both carbon, right, so we're going to compare that versus that. They both have two carbon-carbon bonds, 2CH. And it's a tie, because they both have two carbon-carbon bonds. So then we need to go out to here versus here. So for this one, right, here versus here. Again, this one has two bonds shown, so it's going to be a CH2. This one only has this one bond shown, so it's going to be a CH3. So for there, right, so we have two carbon-carbon bonds, 2CH. This one, we only have one carbon-carbon bond and 3CH. So the carbon-carbon bonds are going to be the heaviest, but this one has two, this one has one. So this is going to, so this group here is going to be a higher priority than this. Right, so here are the highs. Right, are they on the same side? Yes, they are on the same side. So it's in a Z configuration. So very similar to what's going on with the R and S. You're just looking at these two and comparing them to these two. Okay. So next up is going to be the mechanism. So you're going to have either an SN1, SN2, E1, or E2. So we'll go through these but you're only going to get one of them. This way I can get you to study all four. Okay, so I'm going to present it like this. So you have reactants, you have products, and I'm going to tell you which mechanism we want. So for the SN1, for the SN1 and E1, the first step is always going to be the leaving group leaving, okay, to get this intermediate, well, a carbocation intermediate. So that's going to go away. So these two electrons are going to go up onto that bromine to form this new set of lone pairs here. Right? So it has three now it has four. That's where these two are. So for now, right, so this carbon here only has three bonds, so it has a plus charge. And then next, this negative charge is going to be attracted to positive right there. And you're going to end up like that. So how did I know it's going to be the carbon attack and not the nitrogen? Well, just look at the product. So we're making a new carbon-carbon bond, not carbon-nitrogen. So I am going to give you the product. So for the SN2 mechanism, so for the SN1 E1, it happens in two steps. For the SN2 E2, everything happens in one step. Go figure. So for here, again, we're going to be making, right, so here's our leaving group, right, it's going to go away. We're going to be making a new bond between this carbon and that carbon. But everything all happens in one step. So these electrons here are going to do a backside attack there. And then these electrons are going to be coming up to form this new set of lone pairs here. And that's it. So we get, so this comes here, right? This nitrile group is going to do substitution. It's going to swap out for this bromide. when this goes away, it takes the electrons with it to form a new set of lone pairs. Okay, so for the E1, right? So for whenever you see elimination, you know you're going to have to get a double bond on the as a product. Okay, so for here again, this is going to be our leaving group. This is going to be, so that makes this our base. Now for the E1, the first thing that happens, just like the SN1, is that this leaving group is going to leave. And so we're going to end up with, just like the other one, we're going to end up with a positive charge here, right, and a bromide, just like the other, just like that other reaction. Now, if you're stuck here, don't know how you're going to get from here to here, one of the things that you can do is take a look at what the hydrogens are looking like. Okay, so for this carbon here, we have one hydrogen on this side. This carbon, it doesn't have any, right? Because 1, 2, 3, 4 bonds are shown. So the corresponding ones over here, like this. Right? So we have, for this carbon here, we have 3 bonds shown. So there must be a hydrogen here. Well, that corresponds to this hydrogen. But over here, we have 3 bonds. This one, we also have 3 bonds shown. So there's an H here. So we're going to have to get rid of, that hydrogen, as well as this needs to attack something to make water, right? And remember, water, we think of it as HOH. About that. So this OH is going to have to grab one of these hydrogens in order to be able to make the water. So what ends up happening is it's this hydrogen here, right? It's that hydrogen. There. So it's going to make a new bond here. These electrons in this bond here have to go somewhere, and so they're going to collapse right down there to make that. So you know you're going to have to do something at both of these carbons because you've changed both of them. So, but remember, it's going to go in 2 steps. First step is always to go away. You can always go in and draw in the hydrogens, right? So there's the hydrogen there too. Okay. So for E2, right? So just like the SN2, everything has to happen in 1 step. So for here, right? So I drew in this hydrogen, right? That was there. But this one also has, because remember we're dealing with these 2 carbons, right? This one also has a hydrogen because there was only 3 bonds shown, so I had to get it in H. And we're going to be left with no hydrogens here, and then the 1 hydrogen here. So again, we're going to have to remove this hydrogen. So as well as make the water molecule. So remember that's HOH. So what we're going to do is we're going to take this, one of these sets of lone pairs, right, and make a bond with this hydrogen. These electrons have to go somewhere, right, because hydrogen only needs 1 bond. So that's going to collapse down, and then this carbon can't have 5 bonds, right, so it's going to push these away, and everything's going to happen all in 1 step. So in the E1, the leaving group leaves, and then the base attacks. In the the E2 case, what's going to happen is the base attacks and then causes the leaving group to leave. Okay. Now for this one, okay, this one you have to take into account the positioning of things. Okay, so again, it's all going to happen in 1 step because it's an E2 reaction. We have a base, we have our leaving group. Okay, so one of the things we have to do is notice how the leaving group here is in the equatorial position, right? Because the carbon-carbon bonds are pointed straight down. So that means, or down. So that means the axial position. What's in the axial position must be going straight down. So bromine's kind of going off to the side here. So the hydrogen that remains, right? Because there's only 3 bonds shown, must be going straight down. And then we need to think about what's going on either side, right? So here, right, there's the axial's straight up like this, and then we're going to have hydrogens going off to the inside, right? Because there's only two bonds shown, so there must be both CH2 groups, 1 axial, 1 equatorial. The problem comes when this, let's see if I can get this, just show it on the video. So notice how, if this is the bromine, it needs to be the group that needs to be 180 degrees from it. So it would be right here. So you know how see how the bond is coming this way. So so 180 degrees from here needs to be a hydrogen. It's not. It's the CH2 group. Okay? Kind of see that. So 180 degrees from that is this. Not going to work. So what we really need to do is we need to do a chair flip. And so when you do that, this comes down like that. And so now, if you look, see, get this to look, there we go. So now, here is the leaving group. Right here, this would go out to a hydrogen. Okay, it's not a carbon. It's just a regular hydrogen that's coming off of it. Okay, and so what we need to do is we need to say, okay, so if we're going to look at this one, this side, right, there is a here's the leaving group. 180 degrees from it is a hydrogen. So we could make a double bond here. On the other side, let's see again. Let's see if I can get this to go in the video. There we go. Notice how the leaving group is here, and then down below, there's a hydrogen here. So that means on the other side, we could also make a double bond. So as long as there's a hydrogen axial to this, so after the chair flip, remember you start off with these two middle ones, and then you just shift these guys here back and forth. And so if I do, say, 1, 2, 3, 4, 5, 6, okay, so now carbon 1, 2, 3, 4, 5, 6. Okay, so now the bromine is axial, right? Because when you do chair flip, it's still going to stay up, but it's going to goes from equatorial to axial. So now, right, because we had the CH2, you're always going to have an H axial. So this was equatorial. Right, so you could make a double bond here, which would give you, and that's because we have a hydrogen here. That's axial. You can only have a hydrogen here. If that's the case, then we can make the double bond there, plus water Br minus. The other option would be, because remember this is axial too, we could have instead made this one, the double bond here, because that one's axial. So you can go, so you could make the double bond on this side. The problem is going to come, so you have to get this the leaving group axial first, and then you can see, is there an axial hydrogen on this side? Yes, then there's going to be a double bond on that side. If there's a hydrogen on between 1 and 6, there's a on 6 there's an axial hydrogen. So yep, so we can make a double bond between 1 and 6. On between 1 and 2, right, on carbon 2, there's an axial hydrogen after the chair flip, so we can make a double bond between 1 and 2. The problem comes is if you were to have, say, this methyl group be like this. Let's see if you can see this. Okay, so notice how if the methyl group was axial, if we had a methyl group down here instead of the hydrogen, we wouldn't be able to make the double bond here because this is not a hydrogen. Yeah, it has hydrogens on it, but it has to only be a hydrogen, not a methyl group, not an ethyl group, not something else. It has to only be a hydrogen. If that's not the case, then you cannot have a double bond between these two groups. This one would be fine. Okay? So between this leaving group and this hydrogen, so we'd only be able to get the double bond between here. So, okay, good luck. So now I know it's a little crazy, but that's sort of the culmination of all of those things we've learned about with acid-base chemistry, E2 chemistry, and chair flips, stuff like that. So that's what we're looking at. So okay, so for this one, we're going to predict the product. Now I'm going to show the mechanism, but I'm not really, you don't have to show it. I do it because, so that you can see what's happening. So for an SN2, right, we're going to get a substitution. So we need to find our leaving group. So that would be this bromine here. So that makes this our nucleophile. So this is going to take us a set of lone pairs and attack right there, and then push that away. Now when that happens, because it's an SN2 attack, the substitution happens on the back side, so it's going to flip. So if this was on a wedge, that means this this group here is going to be on a dash. So you're going to end up like that. So that's going to be your product plus plus PRs. Now if this was on a dash, then this would be on a wedge. If this was an SN2 reaction, remember, because of the mechanism where the leaving group leaves, that flattens out the carbon, and so half the time the OH would come in from the top, half the time it would come from the bottom. So there you get two products, and each one of those, one where you have the OH as a dash, and one where you have on a wedge. So you get both products, the R and S products, with an SN1. With an SN2, you just get the inversion. So for this one, right? So for it's an E2, right? So you use the same thing, right? This means double carbon double bond. Okay, so again, here's our leaving group. So what we need to do is take a look here, here, and here, and see if there are hydrogens. So if there are, so this one, if we go from, so this one has hydrogens, right? Because there's only one bond shown. So there must be hydrogens here. So we could make a double bond between here. So when we do that, we would end up with a double bond like that. Right? So we rip one of those away, we leave, as well as the bromine. Like that. So we'd end up like that. Now again, so for this one down here, say there is a right, so there's only two bonds shown, so there's at least one hydrogen there. So we're good, so we can make a double bond there. Like that. Just be the one hydrogen left behind. Now we could have also done it here. So for that, but these two are actually the same molecule, right? It's just this flipped. This flipped over, or I guess that flipped over like that. So with that, so it's really only the two products. So for this, you have to tell me what the major product is, and for that, you look for more substitute. So you want to see how many you want to get as few of hydrogens are on there, right? So you've substituted what you've swapped out as many hydrogens as you can directly on the double bond. Okay, so for this one here, this carbon has all four bonds shown, so there's no hydrogens here. But on this side, there's this one and this one. So this one has two hydrogens. For here, again, this one has all four bonds shown. Okay, but this one has the single hydrogen here. So, right, so you want the fewest number of hydrogens on the directly on the double bond. So that's going to be the major part. Okay, so for this one, right, there's two parts. Okay, I'm looking for like aldo triose or keto heptos, whatever. Look at that. So I'm going to need. So you get a point for figuring out if it's a keto or aldo, and then another point for getting the number of carbons correct. Okay, so for this one, right, it's a right, because there's carbons on either side, so this is going to be a keto. Right, and then there's 1, 2, 3, 4, 5, 6. Don't forget that one. 7 total carbons. So you come down here and so you look at this chart, which I'm going to give you on the equation sheets. So it's a keto heptose. Now for this one, right? So here's our carbon-carbon double bond, right? But there's a hydrogen number here, so that makes that's an aldehyde, so it becomes an aldo sugar. And then we're going to go 1, 2, 3, 4, 5, 6. Okay, so that ends up being 6. So hexose. So it's an aldohexose. There you go. okay, so is the sugar in the D or the L configuration? Right. So for these straight chains, all you have to do is look here, here, and here. Right. So if this sugar here, so it's the last chiral center away from the aldehyde. With that, so if it's like this, right? So it's in the D configuration, right? So that means it's going to point to the left or to the right, and for the L's, it's going to point to the left. So like that. So here it's pointing to the left. So this is L. This one is pointing to the right. So it's D. Doesn't matter about any of the other ones. It's just this one. Okay. Now for here, you're going to be looking at this carbon right there. So this one and that one. If it's above the ring, right? So with that, so it's going to be a D. If it's below the ring, it's an L. And so for this one here, this doesn't matter how the this OH is pointed. It's just where this carbon is. So below the ring, right, just like this one, this is going to be L. Above the ring, this is going to be D. So for here, when we say basically draw the enantiomer, what we're going to do is we're going to have to draw the complete mirror image of it. And so you can go like this. So you go. The positioning of this top and bottom one doesn't really matter because they're not chiral, but these in the middle do. And you have to flip all of them. Okay, so going from left, left, right, it needs to go right, right, left. Same thing with this one. So we go right, left, right. So we need to go left, right, left. There we go. Okay, so for the linkages, so one of the things we're going to want to do first thing, right? So we're going to need to get the need to get the numberings, right? So you can mark in your carbons, right? So 6-membered ring, right? So carbon 1 is always here. The one that has the 2 carbon, well, that has the 2 oxygens on it. It's what's called the anomeric position. The other thing you can do is it's a 6-membered ring, so the one squirting out is always the 6 out here. So 6, 5, 4, 3, 2, 1. So you can always go backwards. Now that's if you get to this point and you're at 2, you don't count that. You don't count the oxygen. If you get here to 2 and something's wrong, you've probably either forgotten to count this one or this carbon. Okay? And so they're going to be like this. So, this. And so 6, 5, 4, 3, 2, 1. So for here, so use your carbons. 6, 5, 4, 3, 2, 1. And then for here, 6, 5, 4, 3, 2, 1. Okay, so when you're looking at this, say this linkage here, all you care about are these 2 sugars. Okay? And so you're going to go from the left to the right. Okay? So the left-hand sugar, if this bond here is pointing down, coming away from the left-hand sugar, that's alpha. And so this is an alpha because of that, and going from 1 to 6. So 1 to 6. Now for this linkage, you're only concerned about these 2 sugars. So now this one is the one on the left, and this is on the right. And so since you're concerning about coming away from the left-hand sugar, so this one's going up, right? So it's going to be beta. It's going from 1 to carbon 1 on this side to carbon 4 on this side. So it's going to be 1 to 4. Now for this one, okay, again, you're only going to be concerned about these 2 sugars. This one's on the left. Okay, so this is the left-hand sugar. And so, again, you're going to go from the left to right. So notice how that's pointed down. So that's going to be alpha. And it's going from carbon 2 to carbon 6. So this one goes up, this one goes down. So there you go.